Hello and welcome back, my fellow path integrators. Today a little follow-up to the last video where we calculated the area of a circle. Now we're going to calculate the area of an ellipse, which is kind of just like a circle stretched, if you know what I mean. Alright, if we remember the area of a circle, which is in everyone's of our heads, well, that was weird English, right? So the area of a circle is pi times r squared. And here we already have written the area of an ellipse, which is pi times a times b. It looks quite similar to the area of a circle, where a times b might be something like r squared. But now we have to ask ourselves, what is a and what is b? Well, take a look at the ellipse here on the left side. If you think about a circle has a radius and the radius is constant, but an ellipse does not have a constant radius. So the radius would be the distance between the center and a point on the ellipse. But this distance is always different. So there is no constant distance that we could use for a formula like this or like this. So what we have to do is we have to use some auxiliary elements of the ellipse, and this would be a and b. A and b are the so-called major and minor semi-axis. So let's use another color here. This here would be a. This is the major semi-axis, so the big axis of the ellipse. So major semi-axis. And b, this is the smaller semi-axis, so the minor semi-axis. So we have semi-axis, and above here we write a minor. So this is what we have to do. If we want to calculate the area of an ellipse, we have to know the major and the minor semi-axis. But we want to derive that formula, and we want to derive it in a similar manner as we did for the circle, and we do so by applying integration. So first of all, we remember how a circle has been defined. The definition of a circle was x squared plus y squared is equal to 1. This is due to the Pythagorean theorem. And if we rearrange the terms here in terms of y, then we have y is equal to the square root of 1 minus x squared. So if you take a look at a circle, let's draw a little circle here, then integrating from 0 to r, this function here would lead us to the quarter of the area. So the area of a circle, as we have shown it in the last video, is 4 times the integral from 0 to r over 1 minus x squared dx. Good. Now, how is an ellipse defined? Well, an ellipse is defined via the major and the minor semi-axis, and it is somehow a stretched circle. So the ellipse definition equation looks similar to the circle and involves a and b. And this will look like this. So we have x squared divided by a squared plus y squared divided by b squared is equal to 1. This is the definition of an ellipse. Now we just rearrange some terms, and we get that y is b times the square root of 1 minus x squared divided by a squared. So let's take a look at an ellipse again. So we draw a little ellipse like this here, and this looks ugly, so let's just draw this again. So what we do here, we do a straight line here, and we do a straight line here, and then we're lazy and we're copying this ellipse from above here, paste it here, and here we are with our ellipse. It's not symmetrical, but I think you know where this is going. So here we have 0, here we have a, this is the x-axis, this is the y-axis, and we are going to calculate this area here. So the whole area of the ellipse is 4 times this area here, so 4 times the integral from 0 to a. Then the b is a constant, so we can extract that out of the integral, and then we have 1 minus x squared divided by a squared, and then of course don't forget the dx. So this is the integral that we have to solve. The area of an ellipse is 4 times b times the integral from 0 to a over the square root of 1 minus x squared divided by a squared dx. So how are we going to solve this integral? Well, first of all, we start with a little cool and cute substitution. What are we going to substitute? We're going to substitute this thing here, x squared over a squared, or a bit more simple, x over a. So what we say is u, oh no, that's wrong, u is x over a. So this means if we transform the limits of the integral as well, then we have u of 0 is 0 because we just plug in 0 for x, and u of a is just 1 because we plug in a for x, and then we have a divided by a, and this is just 1. Alright, so we have transformed the limits, but we also need to transform the infinitesimal element dx. So how are we going to do this? Well, we are going to take the derivative of u with respect to x. This will give us 1 over a, and this means that dx is just a times du. So let's plug that into our integral. So we have 4b, then this a here is a constant, so we have 4b times a times the integral. Now the limits of the integral have changed from 0 to 1, and then we have the integral, the integrand, 1 minus u squared, and then of course du. Now let's go to a little different color. If you remember the identity of cosine, so we have and sine, cosine phi, cosine squared of phi plus sine squared of phi is equal to 1. This also means that sine squared of phi is equal to 1 minus cosine squared of phi, and this also means that sine of phi is just equal to 1 minus cosine squared of phi, and then the square root of all of this. But the whole thing also goes backwards, so we can also say that cosine of phi is the square root of 1 minus sine squared of phi. So we can substitute u with cosine or sine, and just because I don't want to deal with minus signs that we get from taking the derivative of a cosine, because the derivative of cosine is minus sine, I'm just substituting u to be the sine of phi. So this is what I'm gonna do. The substitution will be u is equal to sine of phi. And now of course we need to transform the limits of our integral again. So this means that phi is the arc sine of, not of phi, but of u. And this means that phi of 0 means the arc sine of 0 is just 0. So for which x value does sine get 0? Well, for 0, so this is 0. And then for which x value does sine get 1? Well, it's pi over 2. Of course, there are infinitely many values for which the sine gets pi over gets 1, but we are just interested in the angles between 0 and 2 pi. Alright, now we transform the limits. Now we just have to transform the infinitesimal element du once again. So we take the derivative. That word is actually funny. So we take the derivative of u with respect to phi, and now you see what I meant. If we would have substituted it with cosine of phi, then we would have gotten a minus, and then you have to take care so much for the minus signs. If you lose them, then the whole solution in the end is done. So better to avoid those minus signs. It's just a personal preference of mine. Maybe I'm just too anxious about the whole thing. Anyway, so we take the derivative, once again that funny word, we take the derivative of sine of phi with respect to phi. This just gives us the cosine of phi, and this means that du, the infinitesimal element, transforms to cosine of phi times d phi. Alright, now we can plug all of this into our integral, so we have 4 times a times b. I'm sorry for that. Must have fetched a little cold. Alright, so the limits. We need the limits of the integral. So the limit 0 stayed, but the limit 1 turned into pi over 2. So we have this integral here, and then we have the square root, and we plug in the sine. So we have 1 minus sine squared of phi, and then here we have cosine of phi d phi for this infinitesimal element here. Alright, so 1 minus sine squared of phi is cosine of phi, so we have 2 cosines in the integral, so the integral in the end is 4ab times the integral from 0 to pi over 2 over cosine squared of phi d phi. Alright, if you remember from the last video, I just use the antiderivative of cosine of phi, of cosine squared of phi to solve this integral here, to keep it easy. But I thought in this video I'm gonna guide you through actually using the, how do you call the inverse of the product rule for integration? Ah yeah, integrating by parts. I'm gonna guide you how to use, I think you know that I'm not a native English speaker. I'm gonna guide you through how to use integrating by parts to get the antiderivative of cosine squared of phi. This is kind of a basic exercise, but I think, in my opinion, it's very good to repeat this exercise once in a while, because I think while I was studying, I have done this probably 6,000-7,000 times, but still it took me a while to remember a certain trick how to do it. And at some point, like when you do more thorough research, you only just Google integrals and standard antiderivatives, and then you lose a little bit of this ability, you know, to integrate. And I think this is a very important ability, so I'm gonna keep that alive. So this is my goal. Anyway, I've been talking a little bit too much now, so let's go to calculating the antiderivative of the cosine squared of phi d phi. And let's remember quite easily how integrating by part looks like. So we have an integral u prime v, where u prime is the derivative of u and v doesn't have a derivative, and I'm just gonna leave out the infinitesimal elements like dx here because this is not important if we just want to remember how the formula looks. So the integral u prime v is equal to uv minus the integral of uv, and the v gets primed, so the v gets a little derivative. So let's go to the cosine, apply the whole thing to the cosine. So cosine squared is cosine phi times cosine phi, and then we put a d phi here. Now we have to decide which one is u prime and which one is v. Well, actually, it does not matter at all, as you can see. So we can just choose this here to be u prime and this here to be v. Well, if cosine of phi is u prime, what is u? That's simple, it's just sine of phi. So we plug that in. We have sine of phi times cosine of phi minus the integral of, and now we have to take the derivative of v. The derivative of cosine is minus sine, so this minus here gets a plus, and here we have a sine squared of phi d phi. Okay, now you might say, what is that? Now I have a sine squared of phi, like now I have to do the same thing once again. I really don't want to do that. Well, okay. You don't have to do that, because we know from our identity for cosine squared and sine squared that this is just 1 minus, not sine, I'm getting ahead of myself, 1 minus cosine squared of phi. So this whole expression here can be rewritten as sine phi cosine phi plus the integral of d phi minus the integral of cosine squared of phi. And now we're here. What is happening? We have the integral of cosine squared of phi d phi is equal to something minus the integral of cosine squared of phi d phi. And this is exactly the trick that I meant before, which I forgot during my studying years over and over again. And that's why I think it's very important to keep on practicing those simple techniques, because they keep your brain alive somehow. So what I'm gonna do here is, I see that this cosine squared of phi has a minus, so I can just put it to this part, to this side of the equation, and I get 2 times the integral over cosine squared of phi is a long term. So I have 2 times the integral of cosine squared of phi d phi is just sine of phi cosine of phi plus this integral here, which is just phi. And since some of you like to tell me that I forgot the constants, I always drop them because, I don't know, in physics we hardly use them. At least that's what I remember. Please correct me in the comments, because I'm always willing to learn something new. Anyway, so here we are. All we have to do now is put the 2 to the other side, and then we have the actual antiderivative of cosine squared of phi d phi is equal to 1/2 times sine phi cosine phi plus phi. Alright, here we are. Now we just need to calculate the area of the ellipse, and this was here. So we copy the whole thing put it down here right under our antiderivative, so we can easily just plug that in. So we have 4ab times 1/2 times, so we just extracted the 1/2 out, and now we just plug in the limits of our integral. So we have sine of pi over 2 times cosine of pi over 2 plus pi over 2, and then minus sine of 0 cosine of 0, and then we have to subtract minus again, but we can just drop that here, minus 0. We have to subtract 0 again. I'm getting ahead of myself again. I'm sorry. Anyway, so this 1/2 here, this cancels out with this 4, so we have 2ab left. Then we have sine of pi half. Sine of pi half is 1, but cosine of pi half is 0. So the whole term goes to 0. This obviously is also 0, so the only thing that remains is the pi over 2. So what we have here is pi over 2, and then we get pi ab as a final result for the area of the ellipse. Amazing. I love this calculation so much. It's easy, it's straightforward, it uses integrals. I think you know that I love integrals. I mean, the name of this channel is Path Integrator. Anyway, this is the solution. I really hope you like it. Please leave a like. Maybe consider to subscribe to the channel. All of this helps so much with the algorithm. I really don't know what's happening with the algorithm. Let me know what kind of topics you would like me to cover. Let me know what I could improve in the quality of my videos. Let me know everything that you want to tell me in the comments. I'm trying to react to everything, and I really love you guys. See you in the next video. Have fun learning, have fun studying, have fun doing mathematics, and have a nice week or a nice evening. Bye!